Good afternoon, everyone. I hope everyone had a good lunch, and we'll try to make it interesting so that everyone is awake. So, um, my today's session is about, if I'm repeating, about this title: Unifying Diverse Logs and Big Data Systems for Seamless Analysis and Action. And we'll see how large language models and OpenSearch as a vector database helps us here. Just a brief disclaimer that whatever I'm presenting and my thoughts are completely personal and do not represent the views of my company or anyone in specific. So these are the three goals which we'll try to cover in today's session. The first one is, how does the RAG architecture help, particularly in big data environment? Enable us to think what are the different possibilities in RAG architecture, and how, as if you have software experience building different decoupled applications, how can we bring that experience into generative AI ecosystem? Now, there are three parts to it. If you're involved in some of these recent happenings, anyone heard about the company called Databricks? Okay, so it's a big data company. They basically provide managed services around Apache Spark. Now, one of the goals of them is that they want to democratize two things. Particularly, they started with data, big data, and the second part is democratization of machine learning and AI in particular. Their goal is that anyone should be able to leverage data and AI. It should not be in the hands of a few. So they are providing different interfaces, user experiences to enable that. The third blank space which we are seeing is what today's experience is about. It is about democratizing operational optimization. So when you think about, we'll talk about what operational optimization means, but this is our goal. The next question is, how many of you know about what a data engineer does, what big data means in general? Okay, good. So I'll just give a very brief idea. Another question, how many of you have worked with databases? Okay, have idea on what indexes are, what happens? Perfect. So I'll use that analogy to give a very brief explanation. So what happens is, you might have an application, you want to fetch some data. So you use a database and you run the query. It does some indexing, clustering and everything, and it fetches the data back for you. Sometimes you run into performance issues and you run an explain query and you see where it is getting involved into. But when you use databases, it's only a single machine where it is. Maybe you're also involved into clustering, sharding and everything else, which divides it into different other machines. What big data involves is, it's huge data. So a relational database cannot handle it. So that's where, let's say you want to do you have let's say e-commerce data. You want to know how many customers are there for a particular domain like fashion, and you want to know how many purchases they made. Very simple query, you do a join and you get the data and do a count. But what about data which is terabytes in scale, exabytes? Your relational database cannot handle it. So that's what big data does. It runs that query, it exposes it on a SQL like layer, but behind it runs a lot of jobs, kind of optimizations, and these run on separate machines. So when you say about your grouping, your counting, all this happens in different machines, and a central machine collects all this data back, and then it figures out, okay, I'm done with this, what should I do next? So that's where it happens, different jobs, each job might have different stages, each stage might have different tasks, and each task runs on a particular machine. Like you're running a database on a single machine, a task runs on a single machine, kind of. Okay. I hope that gives a very general ideology. Okay. And now this is what it happens. So you're querying it, it collects all the data. If you're doing some sorting, group by, it cannot happen, on a single machine. So let's say you want to read some data. Very simple analogy. You have a group of, let's say, different colors of, M&M chocolates or gems, right? So you want to group them. You want to count which color of chocolate is what, right? The very first thing is you don't know what is there, right? So you know that particular set of data set is there. Let's say 4 groups. You send those 4 groups to 4 machines. And each machine calculates, right? Okay, I got 2 red, 2 oranges, right? Now 4 machines have 4 data sets, but each of them doesn't know, what other counts. So now you need to group and, collect all these together. So all this data gets centered around and finally it gets back, okay? Now, hope everyone has an understanding of, the generative AI ecosystem, or have used ChatGPT. That's the simple question. Now, what happens in the big data environment is you have a notebook here. Basically, everyone heard about Jupyter notebooks? Okay, so that's where, data scientists or anyone in particular big data, they run their, particular commands. Now, when you run into issues, what Databricks provides you is if you see on the right, a very intuitive, ChatGPT kind of interface, but it's very particular to Databricks and Spark. So anything, it has a context. If you write on the left side, you say, I am facing an issue, it will give you an answer on the right. So it gives you context, it gives you that help layer. Now, what the problem is here, this is good for interactive learning, right? You're interacting, you're writing something. But when you run a particular job, right, it runs in the backend somewhere, in some clusters. So you'll face a lot of issues. A very analogical comparison is, let's say, your query is running slow. You run and explain, right? Then you see what is the result, you query, you again do something. But for big data, it's very complex. You have to know a lot of details, partitioning, where is the cluster, what is the cluster size, configuration, enabling certain clustering, indexing, and all this stuff. And if you ask this Databricks assistant at this moment or some, it won't give you the relevant answers because it doesn't know what is happening in your clusters, right? It will give you some general information when you ask about it, but no contextual information. So this is whenever you run a job in Databricks or Spark, you have this interface here, which tells you, what is the Spark job which ran, what is the timeline, if you see an executor got added, if you see the driver is something which executes the job, it gives, assigns the core engines, you do this. So that is how it is happening here. So I'm just showing you the interface of Spark UI. And this is, it says, for how much time a particular job has been running and which engine in particular. And if you see executors are removed, added, it could be due to error, or it could be that, we're auto scaling it. So the job is done, they're just being removed by the driver. And it also gives you other information that, certain tasks have executed. It takes 258 tasks to complete the complete job. And certain, terms here like spill. Spill is something like, let's say you are running a job. The driver decided I'm going to run it across 4 tasks. Each task, has a optimal memory usage. You can say 128 MB, but your data set is kind of, let's say, 200 MB or something, right? So it's spilling across. It's not fitting into your memory. So what your driver or engine is trying is, I'm trying to fit it, but it will, out of memory issues will happen. So these issues happen, right? And it also tells you how much time is taking, what is the max time happening. So it gives you certain, distinct features here. And if you see, this is also a very particular stage which is happening, where it is saying that it's reading around 20 GB of data. So that is where it is spending most of its time. Now, if you saw this, what an experience for a data engineer would be is that sometimes they spend around 5 to 8 hours in terms of finding the problem. leave the solution part apart. It's more about finding the problem. And from my experience, we don't want to spend time finding the problem, right? We want to solve the problems. And if you saw the interface, you can go from one interface to another, see where the issues could be happening. And for this, you'll need some knowledge of how Databricks or Apache Spark works. So you can understand it's a bit complex, right? You should be in a bit of an more than a bit expert level on understanding how things happen, to understand what these metrics are giving you, right? And there are different solutions. So let's say once you find the problem, it could be that you're using a suboptimal cluster configuration, or maybe you're not using certain configurations which could help you, or maybe your data is not in the right structure, right? And these are some of the solutions. So let's say you're doing a lot of joins together and it's not an optimal join. So you can use this configuration which helps you, right? And we are talking about the solution part. The question is about, did you find the right problem? And I'll show you one of the log files whenever you run a particular job. And sometimes it could be a lot of log lines which you have to parse. What the Spark UI does is that it parses a log and it shows you that log information. So that is what it is doing. And you have to read through it, find it, experiment and retry it. This is, if you run it in a local environment, this is how a single file will look like. It just generates a single file. And so I ran a few jobs here in the local environment, and this is how it looks like. If you see the duration of the jobs, right? I just increased some data size here from 2 MB towards 1 GB, and you can see the duration increasing. So if I go into any particular job, I see this is one job, and if you see it took around 1 minute, and if I click on the job here, it's still loading, and it says that there are 2 stages which it's trying to complete. If I go further into a job, it says that taking 16 tasks, and you might see first it is trying to read. The input is around 2 GB at the bottom, and then it has a shuffle of reading. So here you can see it's a lot of tasks here, and we can see in general that it's shuffling a lot of read. So shuffling means transferring data from here so that it connects all together. But I won't go into very detail of here. Now, if I return here, you might see a very general pattern. So this is kind of a JSON-L format. So each line is kind of a JSON format. And if you see, it says, the Spark listener log started, it's a sequence of events. Kind of, these are the activities which are present. So it says an application started, the job started, the stage, it has a hierarchy to it. And this is what it can look like. So a single application generates kind of a single log file. This sometimes can depend on what you're doing. The size of the log file can change here. But it's a sequence and hierarchy of entities if you see. So there's a job has some stages, each stage has some tasks around it. Now what is the solution we are trying to find here is, if you think about it, if you go to the documentation, which I might share here, if you go here, Databricks has a very neat documentation. It says that if you have a problem, first see the sequence of event. If it is too many sequences, or if a lot of servers are going up and down. If you don't see it there, go one layer deep, go into the stage layer, see where it is spending the time. If you have an input of kind of 2 GB, it means you're reading too many files. So then it suggests you, if you're reading too many files, shorten the file, change it to different format. So that is how it suggests you. So an engineer or data engineer would go there and they would read it and they would follow it line by line. As you practice around it, you will know it, okay, this is what I need to do, right? But if you think about it, it takes around, for starters, who are new into this optimization field, at least 3 to 4 hours, because they have to read the document first, then they have to correlate. So there's a contextual change. They have to go to the Spark UI, they have to come here, they have to see, there will change here. Now this is what we are trying to solve here. If you see the information, we can feed the complete log to a large language model. We can instruct it because we know that it's a sequence of events we need to follow. We just need to instruct the large language model, this is my actual log event. I want you to follow these steps and give me where the issue could be. And we could follow this because it's a very sequential event, there's no magic to it. There could be some, but at least in its simplest, we see a logic to it, right? And very similarly, I'm not saying that you should always limit your thinking to this, but you can think like how this case also helps you think about your own practical use cases, where you can bring such a thought process if it's a similar line of ideology. Now, how many of you have an idea on the prompt, what prompt does? Okay, good. So here I'm just giving it because these are the 5 steps with Databricks documentation shares. You go through the jobs timeline, then you see the longest stage. So just stepwise. Now this is kind of an example which I'm providing. And this is what the overall simple architecture looks like. So there is a user query. I'm providing the log or event context to it. Plus there is a prompt to it. The prompt basically says what it should do. It should follow one by one. If it doesn't find a problem at the first step, go to the next step and find relevant information from the log. And the fourth one is I'm also providing it a solution doc, because for every problem there is a solution, like changing a configuration or changing the cluster size, etc. But if you think all of these 4 aspects, eventually it's a simple, if you think about the pro of it, and it's a good starting point. We are very quickly able to establish something to help you out. Some of the cons of it is the latency, right? Because it's going through the large language model. You might not get the exact result because there are a lot of examples which you'll need to provide it. A simple prompt, a one-shot example wouldn't help. You'll need to give it a lot of examples so that it can answer you in such an example. And the third part is the prompt or the context window size. So when you think of the context, we are providing it a lot of information, right? And that might not always help it. And different large language models have different context windows, and it might not fit into your size. So that is another challenge there. So this is the classic RAG example, and this is how it works. You always use embeddings and then match with OpenSearch to get the relevant documents. The question is, could RAG help us here on a next step? And when we think about any RAG architecture, some of the questions we should ask ourselves is, what should be the contextual document? In our case, is it the solution or should it be our logs? What should be the prompt in this example? Because given based on your contextual document, the prompt will also change. And if you use this, what could be the trade-offs? So I think I would suggest these are some of the questions you could start with to approach this. Now, what it does is, Databricks as an environment, it generates these logs. These logs can be connected to your S3 bucket. So whenever these are generated, it's generated in your S3 bucket. So you have reference to it. And you can mention at which path you want to generate it in Databricks. So if you think about this particular architecture, we start from the top, which is automatic, because Databricks, whenever your job runs, it generates these logs in your AWS S3. What we want to use here is the ingestion pipeline of OpenSearch. So what it does is we are using a template of it. So whenever new S3 files are generated, we want to ingest and convert them to embeddings and store it in your OpenSearch vector store. So that constitutes the middle layer, where we have this. And when you are chunking the document into different sizes, one of the other aspects you have to see is how do you correlate or join these together. That's where you have a single job ID, right, which you can add to the metadata layer, so that whenever you get, you can further query it to, have a more fine-grained query. Now this is where the RAG query could come in, where you question, what could be the issue for this particular data which I have. What do you think about it? So this is where this RAG architecture will help you. Now, some of the pros and cons here is we have an improved context window, because we'll always get a very contextualized input. The models could be explored. You can check out different large language models as to which work better for you, because there are two aspects, not only the embedding model but also the RAG, because you have to answer in a very natural language manner. The third is, since we are using now RAG architecture, we have some better groundedness here, because we are having a document reference to it. Now, some of the cons is that the latency increases, because now you're using two large language models. Some of the context could be missing, because when you chunk the document, the relation is breaking. Previously, you had a single document where everything was correlated, but now since you're chunking it, you'll be missing some correlation. So you might not get the appropriate perfect answer. Now, the third aspect to it, how do we improve it? So this is where graphs come in. So graphs can help us in terms of correlating these different aspects of it. So if you see here, it's a very simple graph where a person is related to a movie and there's a relationship for it. And if you see, we also have a relationship in our document, which is, it starts with a job. A job has a number of stages, and each stage has a number of tasks associated to it. And there's an optional part to it on the right, which you see, which is the content or the vector embedding. So I think some of these Neo4j or related graph databases, they also provide you embeddings. So you could also store some of the content there, but that's a very optional layer, because you could also use Amazon Neptune for it, which doesn't have this feature. So given that, this gives you the flexibility to adopt this. Now, how do we improve the pipeline in terms of what we had previously? Now, what happens if you see there's a change in the middle here, which now has this two layers here, where we have included a graph database. So now what happens is, whenever a new file is generated in AWS S3, your AWS Lambda is now passing the relationship. So it can pass the relationship, it can correlate, and this we can store it in a graph database. Now, there are two things which AWS Lambda does. It is storing not only in GraphDB, but it is also generating those embeddings and storing it in your OpenSearch vector store. Now, if you see on the right, when a user queries, we have a prompt where it first generates a query in graph database. So you are using a query, we are getting all the relationships which are relevant to that particular job. So you're getting that job ID plus the task ID and everything. Now with this relationship, you can query your OpenSearch with those metadata, because if you have those metadata for those jobs and tasks, you can very specifically fetch those. And with those correlation, there's one aspect here. We can think that it is very similar to the very first aspect when we fetch the whole log together, because everything was there, right? Now also we are doing the same thing. You will fetch all the tasks, but in two layers. But if you can think about every first task, right, it happens in steps. It doesn't happen in follow. If you saw the problem statement in the very first, we first need to see the job timeline, right? For the job timeline, we don't need the stages. We just need the job information and how much time it took. So we just need the top layer of it, not all the information. So this is where the metadata helps here, where we can make a very specific query to it. So every node or every document could have a type called node, which is, you can think about a job or whether it's a stage information. So you get those contextual information and then try to answer it. And if you think about it, it is helping you incrementally. Because if at the very first step you're able to solve it, you don't need to go to the second or third, fourth step. So you're preventing, fetching a lot of unnecessary information which is not helpful to you. But if you saw about this, it's a good start. We are solving the problem, but we are solving the problem of finding the problem. Okay, so we found the problem, but that doesn't help us because we are trying to improve the user experience of the big data engineers or developers. And you can think about any context. I'm just taking a data engineering experience. We also want to find the solution, right? And it depends. If you're expert, you don't want to use this, fine. We are taking an incremental approach. Whoever wants to use it can use it, right? That's how we approach it. So there's another, if you see on the left, we have added another layer to it. We now also have the solution documents. So whenever you add the solution documents, we also, creating a vector for it. So not only now we can find problems, but for that particular problems, we can get the solutions too, because we know those are very referential once you found the problem on the second step. And you don't need to query them at the same time, because maybe he's an expert, the data engineer, and he doesn't need the solution. He knows the solution. The only thing he wanted to know was the problem. But maybe someone wants to know the solution too. So that's the next step they can approach. They can ask the system to give me the solution. But there's another problem to it. What about dynamism? This whole system is very static, right? We got a documents, but if you think about, I'll give you an example. Let's say you explain query. What you explain documentation does is that it will tell you, okay, maybe fix this, your size should be this size. But based on your data size, that requirement could change, right? So you do some calculation. This number of bytes into this, what is your storage, how much is feeding into the memory, divided by megabytes, gigabytes, something, right? That the large language model won't be able to do here, because it doesn't know that information. And I'll just give you an example here. So based on the solution document, the first 3 steps it recommends is do this change, but if you're still not getting the output, you have to do it manually. So configurations don't work. You have to change those parameters, manually. So you have to see what is the shuffled size, that's one term, how much data is moving, and what is your spill size, kind of the memory spill which is happening. And based on that, what is the total number of workers, so which is T here, some formula, which gives you the optimal size which could be. So if you see, it's calculating total optimal size should be 128 for each cluster, kind of configuration. So based on that, what should be the optimal shuffle partition. So there's some calculation to it, it's simple enough, but I will just pass it through. But you have to think like it's just a very simple calculation where you're trying to see how much data is there, what is your optimal size, and trying to divide it to figure out what should be the optimal number you should use. Now this is where, if you see, we are going into the layer of tool calling. So large language models, specifically if you think some of them like OpenAI, have the ability, if you provide them a tooling layer, to make a call, okay, I need some further information because I cannot calculate it. So what the large language model will do is that it will go to this step, the third step, where it says that now it needs to calculate it manually. So for the manual step, it knows that it needs a tool. So it will then call this Python tool to provide these 2 arguments and get those information back. So this is where the tooling layer comes here, which supplements the RAG architecture. Now we have the solution, but what happens is, I think 60 to 70% the solution doesn't work, or 30 to 40% time, because you run it, you don't see the expected, you try something out. That's the ideal documentation. It's a guideline, but you have to figure out your own solution there. So how do we validate it? So one particular tool is we can also use the Databricks tool. So you can always automate, right? Let's say you figured a database solution. What you can do is you can create different database clusters and apply those configurations to it. But in our case, since you're running across, let's say, terabytes of data, Databricks costs you a lot. You can think like running it for 3 to 4 hours on a machine, it might cost you around, if you're running it for 2-3 days, maybe $6,000 or something around. And maybe we don't have the luxury sometimes to, for that. So what do we do here? We can use synthetic data sets. So this is where you generate similar data patterns which you are using for your customers. Because there is a law of scalability. When you're using this huge amount of data, that's how you correlate. Let's say if you have 2 GB of data, maybe you need this kind of machine. But if you reduce the size, very similarly your machine requirement also reduces. And you can apply your changes to that level now. So now it also helps you with regulations because you're not using customer specific data. You are using some very rough, approximations of the data. So you're also compliant with some of these regulations like GDPR, etc. And your cost also reduces because now you can apply parallelly these solutions to different clusters, right? And very similarly, you can think about, applying it to different databases or different sizes. And here, since we're using very small machines, we can experiment with the solution too. So not only is it giving us the solution, it's also trying those solutions on a particular machine and can give us the, improvement which it has gotten through that. And that's where the top layer comes, where it's, we are using a large language model here to generate some of these synthetic data sets, like compare it and generate it and store it in S3. Now, this is where if you were able to correlate, we are using toolings, we are using to get some feedback. And this is also where you can further improve it by using an agentic layer, because always you might not get the right result. Once you get the result, you can have another layer which validates that by having kind of an evaluation there. And agentic AI also helps you by running them parallelly across different machines. So that's another incremental improvement on top of it. This is just where you have a parent agent, you have different agents working in parallel, and you can have resolution at any point. What we talked about is sometimes if you thought about those 5 steps, you can think about them parallelly also. So it reduces your time, more quickly. So this is one of the outputs which you see when you go through this workflow. So the agent tells you, okay, so it went through the information. It found some of these metrics that there's a shuffle read of 3 GB. So total, kind of 6.4 GB of shuffle data. And this is what it says that, this is the total number of workers in your system because it has the cluster information for me. Now it is able to make this calculation. If you saw these 4 steps which we did for the manual step, so this is through the tooling layer. It was able to calculate that the number of partitions for me should be 50 here based on the calculation of 6400 of the shuffle which is happening. And finally, it suggests based on the documentation that this is the configuration which I can use. Now, this is what the automation looked like. It retrieved the documents, kind of. So some of the results which we are able to see here is that we're able to quickly find the problem at hand. That is where most of the time is spent. And when you think about very particularly about the data engineering aspect, you're paying more for the time spent for the engineer because they're trying to find the problem. And if you use the machines would cost the same, whether you use the small or the large, because if you use a small, you have to use many smalls, which also cost the same. So it's all about reducing that effort and time so that you can focus on the solution part of it. And if you think about if in one line I might say what is the helpful layer, if I'm spending 5 to 8 hours finding a problem and it reduces to 5 to 15 minutes, it's very helpful, right? I don't have to, and we all know how much time it takes into debugging different steps, right? And it's an improvement in one side, and at the same side, you can think that maybe one of my responsibilities are gone here. I don't have, but I think you can spend those better in terms of finding solutions, because maybe problems are not helping you much. Um, so if we thought about this whole experience, some of the other things which we can discuss about the user experience, we can talk about, like, we pack it all together, give it, and let the all the information to the user so that they see it together. But I think it gives you too much memory overload because you cannot handle it. A more step manual, incremental approach is helpful, where first we give them what are the problem statements which it recognizes. Then it gives, I think, a call to action. So I think a call to action is very important. Would you like me to further investigate? Or do you think this is helpful? Because the feedback is very important. If it's an expert engineer, it sees that, okay, it doesn't help him, he can provide it. So it gives feedback to the developers who are working on the system. The third is whether they want to try it and they want to validate it, right? But that costs a bit. So do you want to validate the actual solution? So these are incremental steps, and I think a choice to the engineer at which step they want to stop is helpful, I think. And we talked about feedback, how feedback is helpful in terms whether the system is helping them. And I think open system is a very crucial thing, because we should not close it like, okay, this is a solution, but keep it open. Like, let's say if they don't understand a particular term, if the system suggests this is a configuration which you need to apply, but I don't understand it, can you help me further? So not only it's finding the problem, I need to understand what is the problem, right? More details around it. So this is where it can find more information. And the other part is memory. And we didn't talk about memory in any of the architecture, but if you think, we also need a memory, because maybe we asked it something, it doesn't have a context because it has completely forgotten the previous conversation. So I think we need a memory context here so that it knows what we are talking about in our further conversations with it. And the other part is the experience of your domain knowledge is also important. So I think if collectively your organization is running different loads, all of this information is helpful. If one data engineer in one team has suggested something, feedback, or how it helped them, the similar data could help another team member. So if this data is collected centrally and used in a productive manner, it could be helpful. The other is external data sources. So I think we just talked about Spark, but you might think about there are other resources too, which you can bring about. Let's say other engines, helpful layers, which could improve the the productivity of the system. And the last thing is about observability. Since we have a very complex system, we started simple, and you can start simple, see, improve it if it improves your latency, whatever. But I think observability is very important, because if you're going into agentic, it loops around, you never know where it stops, where your cost is, right? Maybe it's invoking 50 clusters, you never know where it is experimenting. So having guardrails as to how many it can create based on different parameters, and observing, how much time it spends at which step, gives you, how your system is performing without explicit feedback from the users. So this is just a very brief introduction about myself, and there's a short code if anyone wants to use any of these books. Yeah, I think that was it. I'm open to any questions. I'm just seeing if I think I'm good here. Okay. Yeah. I just have one question before you guys have any question for me. I hope you're able to at least take, how this architecture is helping, and how you can think about it incrementally. Starting from prompt engineering, if it doesn't help you, incrementally approach it. And it doesn't only, you don't need to limit it to this use case, but if you think about the helpfulness of it, you can recognize what are the, but this is from my experience, I don't want to spend 5 to 8 hours, finding all this. If the system can give me, I want to apply and I want to, finish my work earlier, right? So that's how you can think about any of the use cases you're working. You just have to see, are you spending some time there? Is it a manual effort? You're following some document that gives you a hint. It can be fed somewhere, and you can follow it similar timeline there. And if you see some of these approaches, right, these are from software practices, right? You have the LLM in the center, but eventually you're using metadata, you're correlating, you're feedbacking, you have observability, right? And all of these are software practices you're bringing into this whole layer. So this leaves it very open, and I'm not saying you just need to follow these. You can experiment, you can bring new patterns to it, which help you. And some of these will be very particular to your use case. What might work here may not for you, but you can experiment around it. Yeah. Okay. Any questions? I hope I didn't overload with this so much content. Okay. Okay, perfect. Thank you so much for your audience.